Hello, everybody. Since I forgot to record yesterday's class, I figured what I would do is make a recording of me going through the notes from yesterday. Since the end of yesterday's class, I've added a couple of examples and clarified another. And if I end up making any changes to these notes as a result of going through them, I'll be doing it in real time during this recording, and then I will update these notes in Canvas in the discussion item for yesterday's class. Okay, so the purpose for the task for today is to start going over sequences, and I'll go all the way through these notes right now, and then continue to find notes on sequences in tomorrow's class. So, what is a sequence? The simplest definition that I can give is an ordered list of numbers. So a set of numbers is inherently unordered, but here we assign an index to each number in a sequence. So the way we would normally write a sequence, here's a notation I use for a generic sequence. It has terms, A1, A2, A3, and so on. So a generic element of a sequence is described as A sub n. So the index of each number in a sequence is written as a subscript. Now, some terminology. Each number in the sequence, A1, A2, or A3, those are called the terms of a sequence. So when I refer to a term of a sequence, that's what I'm talking about, just one of these numbers. Most of the time, a sequence will be described as being indexed with positive integers, 1, 2, 3, and so on, or what most people refer to as the natural numbers. On some occasions, numbers starting at 0. It just depends on the context, really. But the point is, we're using natural numbers or whole numbers to that are associated with each of the numbers in a sequence to impose an ordering. Now, there are different ways of describing all of the terms of a sequence. So I'm going to show you some examples to give an idea of the different ways that these terms can be defined. So for instance, all even natural numbers, so 2, 4, 6, 8, can be described using a formula like this. So the nth element of a sequence would be the nth even number, which is just 2 times n. So we set n equal 1, we get 2, n equal 2, we get 4, n equal 3, we get 6, and so on. For all natural numbers, so n greater or equal to 1. So that's what typical way to describe a sequence like this. You just give a formula for a sub n. A sequence can also be described in a more concise manner this way, where you take the formula and you put it in curly braces, and then off to the right, we indicate the indices, n going from 1 to infinity. So on the one hand, this notation is more concise. On the other hand, there's no variable associated with these terms to refer to them later. So it's a trade-off as to which notation you use. Most of the time I'll use this kind of description. Another example, odd natural numbers. So we have a sub n is 2n minus 1, so we set n equal 1, and we get 1. N equals 2 gives us 3, n equals 3 gives us 5, and so on. And then this kind of description here is similar to the other one. All right. As I mentioned before, usually we'll index the terms as 1, 2, 3, 4, and so on. Now, these kind of descriptions of sequences are called explicit or closed form. In other words, we have you can think of this kind of description as as describing a sequence as a function of the index n. You plug in n, you get a value, whatever n you want. Another way of describing a sequence is recursively. You describe each term in terms of previous terms. So an plus 1 is defined in terms of a sub n. Now, okay. In order for that to work, though, if we want the first term of a sequence to be A1, we need to specify what A1 is. So as what's called an initial condition, okay, so A1 will be equal to 1. Then A2 is obtained from A1 using this formula. Then A3 from A2, A4 from A3, and so on. So then, to just obtain all the elements of a sequence, we just keep going. So when I set A1 equal to 1, in other words, we're setting n equal 1 throughout this equation. So then I get A2 is equal to A1 over 2 plus 1 over A1. And since A1 is equal to 1, if I plug in 1 here and here, I'm going to get 1/2 plus 1, so I'll get 1.5. Then I'll take 1.5 and plug that in here. So I'm going to get 3/4 plus 2/3, which works out to the common denominator 17 over 12. So that's 1.416 repeating. Note the bar here. And this can continue. In fact, if I were to, I'm gonna cheat for a second here and go to another window, compute the next element, A4. Okay, so the first several decimal places. Paste that in here. Okay, this number is actually very close to the square root of 2. In fact, that's what's happening with the sequence is the terms of a sequence do in fact converge to the square root of 2. So I've just answered this question right here. I'll just make a note of that. In fact, I'll just paste that in here, the value of that. So you can see just by getting to A4, we're already quite close to that value. And as an aside, the formula for the n term of sequence, actually n plus 1 in terms of an, applying what is called Newton's method, which in general is given by this iteration. Okay. And the purpose of Newton's method is to compute a root of a function. In this case, f of x is x squared over 2. Okay. So by filling in f of x equals x squared minus 2 in its derivative down here and simplifying as much as we can, this iteration falls out. This iteration is derived by finding the tangent line to the graph of f of x at the point xn, and then computing xn plus 1, which is the x-intercept of that tangent line. So the idea is you approximate the root of f of x by by first approximating f of x by its own tangent line and then finding a root of that. The idea being that the closer you are to the root, the better approximation a tangent line is, and then the better its x-intercept is at finding at approximating the true root, and it works quite well. I'll be teaching about this method in Math 460 numerical analysis, which I'll be teaching in the fall. That was a digression. The reason I'm introducing is to show how to recursively define a sequence, define each term in terms of a previous term. Okay. Now, in that example, each term was defined in terms of just the previous term and nothing else, no other terms. But you're not restricted to that. You could define each term using more than one preceding term. And we dealt with this kind of sequence in the last Wednesday's class, the Fibonacci sequence. So actually that should be 0. Okay. So if I specify the first two Fibonacci numbers to be 0 and 1, and then define each new one in terms of a previous two, this is called a 3-term recurrence relation because there are 3 terms in this equation of a new term and of a 2 that it depends on. And you could define any kind of recurrence relation that defines a new term of a sequence in terms of however many prior terms, as long as you have enough initial conditions. So however many it depends on, that's how many initial values you need. Because if I want to compute F2, I need F1 and F0. Oh, wow, all kinds of wrong here. Okay. And sure enough, here are those values specified for initial conditions. All right. Okay. Now, what I had done in Wednesday's class was derived an explicit formula for Fn, and here's that formula again. We also say that this expression is in closed form, so we could define Fn without referring to any previous terms. But it's not always easy to obtain this kind of formula. When each term depends linearly on the rest, it can always be done. But my previous example from Newton's method, it would be much more difficult to get an explicit formula for the terms of that sequence. Okay, so now that I've shown you some sequences and different ways of describing them, why do we even have them? Well, for one thing, we're going to spend a lot of time working on infinite series, and particularly power series. Power series have a lot of applications for approximating various quantities. So they play a large role in my specialty field of numerical analysis, and also partial differential equations is they play a key role there. And in order to even define what a series is, we need the concept of a sequence. So that'll be an immediate application for this class. But also, as the example of Newton's method shows, there are times where you're computing something using an iterative process. And that's not something you're accustomed to in the classes that you've taken so far. The problems that you normally solve, you're carrying out a finite sequence of steps and out pops the answer. But in many applications, that's not how it works. What you do is you make some initial approximation, and then you have some algorithm for approving that approximation. And if you were to carry that out infinitely many times, then you would get the exact result. But of course, you're going to have to stop sometime. But so what we're doing though is we're generating a sequence of approximations, and if we could describe that sequence by whatever means, we can analyze its behavior. We can determine, is a sequence going to converge to the exact value, under what circumstances, things like that. So Newton's method from a prior example is one instance of that. Okay. Now, there are cases where it is helpful to recognize that certain numbers are elements of a sequence and use those numbers to be able to describe what the sequence is in general. So you may be given numbers that are a few terms of a sequence, and you want to be able to describe any term of that sequence from the numbers that you have. You may have worked out problems like this, like in puzzle sections of magazines or whatever. I know it's kind of old-fashioned on my part, but where you're given a few numbers, you figure out the next one. You may have had to work out problems like that before. And while that sounds frivolous, I will point out that sometimes in my own research, I've had to have some expression that comes about by whatever means, and I need to recognize, oh, that's a sequence, and now I know more about how those numbers behave, and that helps me move forward with whatever I'm doing. So, so that actually is a real application, being able to recognize a sequence and work with it. Now, given any old selection of numbers, it can be quite difficult in some cases to figure out what sequence they described. But there are some tips that I can give you, and then that'll help with whatever homework problems we have in this area, and then I'll go through a few examples. One tip is do the terms alternate in sign. If they do, then you should have a factor of -1 to the n, because when it's even, this is equal to 1, and when n is odd, it's equal to -1. So it just bounces back and forth between -1 and 1, creating this alternating sign pattern. So that should be a factor in your formula for the term an if the terms keep flipping signs. Now, if you examine consecutive terms in your mystery sequence, how do you get from one term to the next? Are you adding something? Are you multiplying by something? So in the case of multiplying by something, like you see that some term or part of a term, if there's a constant ratio, then you're going to have an exponential. So for example, if you keep multiplying by 3 to get to the next number, then you should have 3 to the n in there somewhere. Similarly, if you keep adding something to get from one number to the next, then you're going to have a multiple of n that in your formula. So for instance, if you start with some number and you keep adding 4 to it, then a general description of that sequence would be 4n plus some number. And that could be determined like by the first one. And certainly these tips will help you with whatever homework problems we have in recognizing sequences. So now I'll do some examples. Okay. So here are the numbers that were given. So 2 7s, 4 over 21, 8 over 63, 16 over 189. So what changes when you go from one number to the next? If it's a fraction, it's a good idea to examine the numerator and denominator separately, because they, of course, could behave very differently. So look at the numerators. We have 2, 4, 8, 16. You keep doubling. So there's a ratio of 2. And then from denominator, 7 to 21, 63 to 189, we keep multiplying by 3. In other words, you're getting from one element to the next by multiplying by 2 and dividing by 3. In other words, you're multiplying by 2/3. So A2 is A1 times 2/3. A3 is A2 times 2/3, and so on. So if I want to describe all of these, A2, A3, A4, in terms of A1, I can apply this relationship repeatedly. Like I can replace A2 in here with A1 times 2/3. So now I have A1 times 2/3 the quantity squared. And then I can take that and substitute it for A3 in here, and I get A4 is equal to A1 times 2/3 quantity cubed. In other words, so that's what I've done here. So in general, AN is equal to A1 times 2/3 to the n minus 1 power. And to get the rest of the formula, I have a value of A1, it's 2/7. So I can just substitute that in here, and I have 2 times 2 to the n minus 1. I can add the exponents, so I just get 2 to the n up top, and then I have this down below. So now we have a formula for all the terms in the sequence. So this is an example of what's called a geometric progression. So when you keep multiplying by a certain number to get from one term to the next, that's a geometric progression. Next example. Here are the numbers that were given. Like before, you see what happens as you go from one term to the next. If you look at here, this is not a fraction. It may be necessary to rewrite this as a fraction that's not in lowest terms to see what make sure of a pattern. But for now, we'll use these numbers to try to figure out what that pattern is. As we go from one numerator to the next, you keep adding 5. If you look at the denominators, you keep adding 3. Now, there are different ways to figure out how to get from one number to the next, but you want a pattern that is consistent. And for homework problems, chances are the simplest numbers possible are ones that are going to work. So for each of the numerator and denominator, we have what's called an arithmetic progression. So since we keep adding 5 in each numerator, the numerator has the form 5n plus b, where currently we don't know b. In the denominators, we're adding 3, so that gives us 3n plus some other number c that also is unknown. So to figure out b and c, what we can do is substitute a value of n and substitute the value of an from one of these, and we can solve for b and c. So we'll go ahead and set n equal 2. So we have a2 on the left side, 13 over 11, and then we have n equal 2 substituted over here. So we have 13 is 10 plus b, and then 11 is 6 plus c, and we can use, so now we have 2 equations that we can solve for b and c. So 13 is 10 plus b, that means b is 3. 11 is 6 plus c, so that means that c would be 5. So to check that, I can set n equal 1, 2, 3, and 4. And sure enough, all of the numbers given can be expressed using this formula. Even for a case of n equal 1, if I put n equal 1, I get 8 over 8, which is 1. And sure enough, that matches a1 equal to 1. So how you get from one number to the next gives you part of a formula, and then you can use the terms that you're given to solve for what's missing. And then get the full formula from there. Okay. One more example. This is one I actually had from class yesterday. So we see we're alternating in sign. So that suggests that there's -1 to the n factor in there. But we're actually going to use -1 to the n plus 1. And the reason for that is when n is equal to 1, we want a positive result. So because -1 to the n, when n equals 1, is negative. So we negate it, which is equivalent to writing -1 to the n plus 1. So this starts you off being positive. Okay. Now we need to figure out if we can set aside the sign changes and just focus on the absolute values of each of these. We can examine the numerator and denominator as in the previous examples. So what happens, what change are we making to get from 32 to 128 or from 7 to 10? If you multiply 32 by 4, you get 128. Both of these are powers of 2. And then we can get from 7 to 10 by adding 3. Now, those aren't the only ways to get to those numbers. Like we can take 7 and multiply by 10 over 7, or we can get from 32 to 128 by adding 96. So which way works? We don't have any other data to check which pattern is the right one because these ought to be written as fractions and we don't know how. So in this case, you could say there's a little bit of trial and error involved. So we're going to try the simplest pattern possible, adding 3 in the denominators, multiplying by 4 in the numerators, see if it works. If it doesn't work for describing the rest of the terms, then we know we've messed up and we need to back up. Unfortunately, it does happen. Okay. So if we describe the denominators as free n plus b for some b, because the last two denominators differ by 3, then we need to figure out what this b is. So we go to A4, the denominator is 10, so free n plus b is equal to 10, and that gives us b equal to -2. Now to check that, we look at A3. So the denominator in A3 should be free n plus b when n is equal to 3. So we plug in n equal 3, we use the value of b that we got from A4, and we get 7, and that is the denominator, so that works. Now, if A1 and A2 were to fit this pattern also, for A2, we would expect the denominator to be 3 times 2 minus 2, which would be 4. But A2 is equal to -2. So what we do is we rewrite it as a fraction. Instead of -2, we write -8/4. And now that denominator fits the pattern. And then we can rewrite A1 as 2/1. So the denominators are 1, 4, 7, and 10. They all fit that pattern. They're equal to 3n minus 2. So that works out. Now, what about the numerators? Now that the first two terms have been rewritten as fractions, the numerators are 2, 8, 32, and 128. Those are all odd powers of 2. And see, we multiply by 4 to get each new one. So there are 2 to the first, 2 cubed, 2 to the fifth, 2 to the seventh. So we can describe the sequence this way. The denominators are 3n minus 2. We have the sign flipping accomplished here, and then an odd power of 2 in the numerator, and that is our sequence. Okay. Now, so one very important task of sequences is to determine, does a given sequence converge to a limit, or does it diverge? Now, I'll be showing you some examples in which we'll figure out the limit of a sequence if it exists. If there is no limit, there are different possibilities for behavior. For instance, the terms of sequence could go up to plus or minus infinity. Or they could be oscillating back and forth between two values. For instance, -1 to the n, that is a sequence that does not converge because the values keep bouncing back and forth between -1 and 1. So if the sequence does anything other than converging to a specific value, we say the sequence diverges. Okay. Now, as an example of a sequence, I'm going to rewrite this in a way where it's easier to see how it behaves how the terms behave as n goes to infinity. So what I'm going to do is I'm going to notice that the first terms in numerator and denominator are the same, n squared. So what I'm going to do is I'm going to add and subtract the other terms in the denominator. So I'm going to add 2n plus 1, and I'm going to subtract 2n plus 1. And the reason for that is now I have these expressions being the same, and I can break this up into two fractions, and this is just going to become 1. And then I'm going to simplify the rest as much as I can. So now I have this, but then n squared plus 2n plus 1 it's good to be able to recognize that this expression is actually a perfect square. It's n plus 1 quantity squared. So now I'm going to simplify this a little further, and I get 1 minus 1 over n plus 1. So what happens in terms of this sequence as n goes to infinity? The denominator here gets larger and larger, while the numerator is fixed at 1. So this number, 1 over n plus 1, is going to get smaller and smaller, eventually converging to 0. So the terms of this sequence converge to 1. So another way of putting it is I can make this number, 1 over n plus 1, as small as I like. So within any distance epsilon greater than 0, for no matter how small epsilon is, as long as it's still positive, I can find an n that makes this number smaller than epsilon. And here's how I could do that. I could say if I if I pick a value of epsilon, no matter how small it is, I can choose an n that is larger than this, and then this number will be that small. So because I can make this as small as I want, that means that this number can be made as close to 1 as I want, just by choosing n large enough. Therefore, the limit of the terms of the sequence is 1. This is the formal definition of convergence of a sequence to a limit. Now, I didn't mention this in class yesterday just because it's not a definition we're actually going to be making use of. It's not something that's going to show up on homework problems or a test. But for those of you who might be interested, I want to make you aware of it. Okay. So the idea is that we can make the terms of a sequence as close as we want to some value L, just by choosing n large enough. And once n is large enough, these values remain that close to the value L that's the limit. So if this happens, for any distance epsilon, no matter how small that is, then we can say that the sequence converges to the limit L. So those of you math majors, if you ever take real analysis, well, if a math major, you have to take real analysis, you'll see this you probably won't see this definition again until then. Okay. If a sequence does not converge to a limit L for any reason, then we say that the sequence is divergent. Okay. As another example, here's our formula for a sub n. What I do is I want to make the numerator have n plus 2 quantity squared, which is n squared plus 4n plus 4. So what I'll do is I'll add and subtract 4. So now I have n plus 2 quantity squared over n plus 2. So that simplifies to n plus 2. And then everything else goes into this fraction here. Now what happens as n goes to infinity? Well, this is getting smaller. It's going to 0, just like in the previous example. But this part is going to infinity. So these numbers can get as large as I want just by choosing n large enough. Therefore, this it's not going to converge to a limit. This sequence is divergent. The terms go to infinity. And this is a formal definition of what it means for a sequence to go to infinity. But it's not something that we'll be needing for working out problems involving convergent or divergent sequences. The way that we will figure out whether a sequence converges and if it's so, what the limit is through techniques that you last saw in Calculus 1, where you were finding limit of a function f of x as x goes to infinity. So all those techniques apply here because a sequence can be thought of as a function, which is of a domain consists of natural numbers instead of all real numbers. So if a function f of x has a limit L as x goes to infinity, and you define a sequence by evaluating f at the natural numbers, that gives you a sequence, then the sequence is going to have the same limit as the function. So given a sequence, you want at least one is defined explicitly, and you want to figure out if it has a limit, think of it as a function. And does the function have a limit as its argument goes to infinity? So all the limit laws that you learned in Calculus 1, as well as any other limit finding techniques, you can make use of. So let's see how much I have left. Okay. So I have a couple examples that I'll show you, and we'll be seeing more examples on Wednesday. So here we have a given sequence, and we can relate this sequence to this function f of x. And notice that the definition is the same, but just replacing n by x throughout. So one way to figure out the limit is to find the highest power of x in the whole fraction, which is x cubed, and then you divide the numerator and denominator by that power of x. So if I divide the numerator by x cubed and the denominator by x cubed and simplify each term as much as possible, then this is what we get. So we have 2x cubed over x cubed gives us 2. 3x squared over x cubed is 3 over x, and so on. And all of these terms, as x goes to infinity, will go to 0, and all these terms also. And you're left with the coefficients of the leading terms. So whenever the degree of the top and the bottom is the same, the limit is just a ratio of the coefficients, 2 to 1. So in this case, the limit of a function, f of x, is 2. Therefore, the limit of a sequence is also 2. Okay. Here's another sequence. And this expression, as n goes to infinity, each individual square root is also going to infinity. So you think of this as infinity minus infinity, which is an indeterminate form. It may or may not converge to a limit. We need to do some algebraic manipulation on this to find out what kind of infinity minus infinity this is. So again, we think of this as a function f of x and see what happens as x goes to infinity. What you do is you multiply and divide by the conjugate. So the conjugate is obtained by replacing whatever sign you have in between with the opposite sign. So we have the sum of square roots here to go with, as opposed to the difference of square roots here. And you have to keep the overall expression the same, so you must multiply and divide by the same expression. And now you can think of this as a minus b times a plus b. But as you know, that is a squared minus b squared, where a and b are the square roots. By squaring them both, the square roots are canceled out. So now we have x squared plus 1 minus x squared minus 1. You can simplify the numerator, and so we just have 2 up top. And now we still have this denominator to deal with. What happens with this as x goes to infinity? So one thing you can do is if I take the denominator, and within the denominator, actually, I'm going to put an intermediate step in here so you can see what's going on. So in the denominator, I'm going to multiply by absolute value of x over itself. Now, the absolute value of x in the numerator, I'm going to leave right here. The absolute value of x in the denominator, I can write that absolute value of x is the same as the square root of x squared. And now I can move this, combine this square root with each of these. So when I simplify, I can have x squared plus 1 over x squared. Well, that's 1 plus 1 over x squared from in here. And then we have 1 minus 1 over x squared in here. As x goes to infinity, these fractions are both going to 0. So I'm left with 2 over absolute value of x, and as x is going to infinity. Well, if the numerator fixed as a constant and the denominator becoming infinite, this function is converging to 0. So we can conclude that the limit of a sequence, which is also the limit of a function, is 0. Okay. Now, one other thing that came up in class yesterday is that if we go back to, for instance, this example right here, the limit could also have been found using L'Hopital's rule. So if you have a fraction that becomes an indeterminate form as n goes to infinity, because as n goes to infinity, the numerator and the denominator, they are both going to infinity. So you have infinity over infinity. When you have that kind of situation, you may use L'Hopital's rule to take the derivative of a numerator and denominator separately. And if you were to do that with this sequence here, you may in this case, you'd have to carry out L'Hopital's rule multiple times so continuing to take derivatives of this, but you would arrive at the same conclusion. Okay, and if I cheat and take a quick peek at the notes that I'll be going through tomorrow. Okay. Yes. So L'Hopital's rule is mentioned in those notes too. So we will be seeing more of that. Okay. So we still have more material on sequences coming up tomorrow. Determining if sequences can other ways of determining if sequences converge or not. And then after that, next week we'll be getting into series. So hopefully this recording helps. Sorry about forgetting last time. I guess I'll have to ask you all to remind me to record at the start of each class. So these updated notes I will now get posted in Canvas.